In this lecture, we'll be introducing you to the Intel IA32 architecture. This is by far the most common architecture that you'll come across in the PC world. A lot of machines now are 64-bit architecture, so if you happen to be working on one of those during this course, not to worry, because there's full backwards compatibility with the 32-bit architectures. Also, I mean, most of the instructions are the same. It's just there's a number of things that are a little bit easier to deal with on 32-bit. A few other names, if you're new to this architecture, you'll hear this referred to as x86 or i386, but it's all referring to the same architecture family. So, brief history. This has been around for a long time. 1985 is when the 386 was introduced, and it was the first architecture in this family. Many generations of processors have come out since then. Xeons, the Nehalem architecture, Sandy Bridge, the Core 2s. I mean, all these, a lot has evolved, and new instructions have come about since then. But the actual architecture is derived from the 16-bit 286 architecture, actually. The 64-bit implementations forked into the IA64 and AMD 64 several years ago. But again, we'll just be focusing on the 32-bit one in this class and lecture. If you want more detailed information, I would highly recommend downloading these manuals. This lecture isn't going to get into all of the nitty-gritty details. The real goal here is just to sort of introduce you to the architecture, the assembly language, to kind of give you a familiarity so you can be successful doing your reverse engineering. But if you go to the website listed here, they actually have a single PDF now that has all of these volumes contained. It's 3,000-some pages, so you know, pretty much anything you want to find out, you'll be able to find within these documents. So I would encourage you to download them, and then if there's things that I talk about during this lecture that don't make sense or you want more information on, this is really your go-to resource. So as far as syntax, there's two main ones that you'll come across. There's AT&T and Intel. There's the two main differences you'll see right away has to do with the source and destination. In AT&T, you have the source preceding the destination. So like in this example here, you're moving the constant value 4 into the EAX register. And then, whereas in the next instruction, you're writing 4 to the actual memory address pointed to by EAX. It's flip-flopped in the Intel syntax. The other difference is that you don't have the $sign and percent prefixes. And so this really comes into play based on what tools you're using. If you're writing assembly, this matters. If you're reverse engineering, it doesn't really matter, but if you, with the exception of just knowing which is the source and which is the destination. So in the 32-bit architecture, we have registers. This is processor memory. In your assembly code, you can directly reference these by name. So these are very fast and efficient. So if you're hand-coding assembly, it's much faster, of course, to store something in a register than it is to write to RAM. This is true in any processor. With when you're assigning it to registers, that's going to be your fastest memory. We have, and we'll talk more about this in a little bit, different kinds of registers that you're used, and we'll be going through these next. So we have the main ones that you're going to see in your coding and reverse engineering are the general purpose registers, which you see here. These are all 32-bit. There's also 16-bit segment registers. I'll talk a little bit later about how the segmentation memory management model works. And then we also have a couple special registers, the E flags and the instruction pointer. That's EIP. And I'll explain those too. So first with the general purpose registers, these can be used for anything you want them to actually, but there's sort of special use cases, conventions that you'll see. So for example, with EAX, often used in the result of a function call. It'll get passed into EAX. And that's why after a lot of calls, you might see a test EAX, or it's moving EAX into a variable on the stack or elsewhere. And so when you see that convention, it's using the results. But there's not a specific rule that says EAX can only be used for one thing. EBX, same goes for the rest of these here. Where these specific cases come into play are on certain instructions. They will affect specific registers. Like, for example, in string operations, your source and destination is typically referenced from ESI to EDI. Variables or instructions that are doing some sort of loop, ECX is typically the counter variable. And so EBP and ESP are also treated specially. In some obfuscated code, you'll see unconventional uses of these registers, but in the 99% of code, EBP is going to be referencing the stack base pointer, and the ESP is going to be pointing to the top of the stack. So, and so each time you have a call, you're going to have EBP is going to be the sort of the base of your stack, and as data items are pushed on or pop up the stack, that's going to be adjusting ESP accordingly. These registers will also be used to reference parameters, arguments passed into the function, as well as some local variables. And you'll typically see that referenced from EBP, since it's the base pointer. That's just a typical convention. EIP is a special instruction. This one cannot be used in any general case, and you can't even really modify it directly. It's altered by these special instructions only. So that you have your jump, which is your branching instructions. You have your call, return. IRED is just the return from interrupt. These are the only things that will actually adjust the instruction pointer. And later in the course, when we get to talking about exploitation, one of the things that you're trying to do is gain control of the EIP so that you can divert execution to code that you control, or some place in memory where you have instructions that you want to execute. The eFlags register, a lot of instructions, in particular the conditional execution, are going to be checking whether certain flags are set in this eFlags. There's a whole variety. We're not going to talk about all of them here. For that, you can reference the manual. But some of the important flags that come up most often, your carry flag, parity, zero, sign flag, overflow. These are used often, and so often, the result of whether it's a call or maybe a loop where there's some math and different operations occurring, you'll see jump of not zero, or jump of zero, or jump of below or equal. These are all, when that instruction executes, it's actually checking the eFlags register to see, okay, is the zero flag set? If it is, then the condition is true. If not, it's false. And so in the manual, one of the things that you'll see for each instruction, it will say what flags are affected by that instruction. And so it's a good reference to see what are potential side effects of a given instruction. All right, there's three main memory management models. We're just going to talk about this segmented model. There's also flat and real, but you can read the manuals for more details on those. In the typical segmented model, you have your large linear address space in memory, and that's broken up into different segments. Typically, in different segments, you might have different processes running, and so you essentially have segment selector, which indicates, okay, this is the segment, and then you have some offset within that segment. So EIP is a 32-bit pointer to the offset in the current code segment, for example. And then what you don't see is that, okay, that then translates to some area in the linear address space. So pretty straightforward. The different segment registers, there's the CS, the code segment. This is altered implicitly by calls, exceptions. You can actually directly manipulate this segment register. You have the data segment, DS, stack segment. But the stack segment you can actually alter explicitly. And that's if you have a special case where you're wanting to have multiple stacks set up in different segments. Makes that possible. There's also these other segments, the ES, FS, GS. These are just for data. One note, we're not really talking about 64-bit, but in the 64-bit architecture, all these segment registers except for FS and GS are assumed to be 0. So that's just a quick side note in case you happen to be looking at 64-bit code at some point and you're wondering how the segment registers come into play. Some of the other registers in the processor, you have floating point registers, MMX and XMM. These are 64-bit and 128-bit pack registers used by SIMD, single instruction, multiple data instructions. Probably aren't going to be dealing with these in this course, but good to know about. We also have control registers, which are the current operating mode of the processor. I mean, one of the things that's common, CR3 points to the current page directory table pointer for the running process. The Intel manual goes into a little bit more detail about control registers, and operating systems may make different use of these. You also have system table pointers, so like the local descriptor table, interrupt descriptor, global descriptor table. These are managed by the operating system typically, and so you may not be messing with these directly in your coding, but that's what these are for. Debug registers will certainly come up in this course. These are setting user for hardware breakpoints. DR4 and 5 are actually referred to as DR6 and 7. That's why there's sort of a skip there. But as far as setting breakpoints, you'll use DR0 through DR3. The others are has different information about the type of breakpoint that's being set in the others, and etc. Again, check the manual if you want to understand all the nitty-gritties behind those registers. You'll also come across some alternate names. In particular, if you want to refer to the lower 16 bits of EAX, for example, you can refer to that as AX. And likewise, the low and high byte of AX can be referenced by AH and AL. Most of your code, you're just going to be seeing the 32-bit registers, but sometimes you may see manipulation done with different bytes, especially like in different encoding, or if somebody's trying to do something tricky with obfuscation, they may be manipulating the other registers. So I mentioned this before, but wanted to reemphasize that with certain registers like EIP can't be an operand. Again, the reason for this is because EIP is always pointing to the next instruction or next address to execute from. And so it is altered by things like the call, the jump instruction, etc. So it can't even be a source operand. You can't say move EAX EIP to try to assign EAX the current instruction pointer. There are little tricks, and we'll talk more about these later in the course, but one common one, for example, is if you have a call instruction to the very next instruction, and then pop off the top of the stack, because when you do a call pushes the return address onto the stack, and so then if you have a pop instruction, well, that's going to pop the return address off into whatever your destination register is. And so that's one way of, if you want to get the current instruction pointer, that you can get it without directly referencing EIP. But again, that kind of sticks out, and some malware and self-modifying code will do that specific trick. And so when you see that, it's kind of a red flag that this probably wasn't code generated by a compiler. All right, so instructions, again, operate on registers, immediates, and memory addresses. Immediates are just literal constant values, like 4, let me see here. And then memory addresses, and in the Intel syntax, you have the brackets around them. So that, you see bracket EAX, close bracket, that's saying the memory pointed to by the address in EAX. Whereas above, we're just assigning 4 to the register EAX. This just describes how source and destinations can be addressed. You'll notice that you can't have an immediate as a destination. That's the main difference, for obvious reasons. As far as operand addressing, this really comes into play when you're dealing with single-dimensional, two-dimensional arrays. This kind of gives a efficient way of referencing different elements within an array depending on the size, and that's where the scale comes into play. And so down here at the bottom of the screen, you see an example where we're assigning to EAX the offset computed by ESI plus ECX times 4 plus 4. And so again, this is most common when you're dealing with arrays or other data structures where this is an efficient way of computing the offset that you want. Or if you have a loop, for example, and ECX is being incremented throughout that loop, then you're going to be traversing an array. All right, so data types, pretty self-explanatory here. We have bytes, words, double words, quad words, double quad words. Most of what you're going to be dealing with are double words, of course, since we're focused on the 32-bit architecture. But you may use other registers that are larger than 32 bits, of course. So we're just going to go through kind of a set of the most common instructions that you're going to incur. Again, this isn't an exhaustive list, and I'm probably going to be going through this fairly quickly. So in the manuals I pointed out earlier, it has an exhaustive listing of all the instructions and every detail about what that instruction does and what its side effects are and what flags are affected. But this is just to kind of give you an introduction to the most common ones that you're going to see all the time. So the first one is the move instruction. This one, as the name implies, is just simply assigning a value. In this case, it's moving 4 to EAX. So it's pretty simple. No op, this one doesn't do anything. It's no operation. And so this one actually comes into play quite a bit in reverse engineering and exploitation. We'll talk about NOP SUDs later. But it also, for example, if you're modifying a program or editing it, or you want to change how a program behaves, or maybe you don't want it to perform a certain action, you can overwrite the bytes directly with no ops, which essentially wipes that code out, and as a way of making it not take a particular jump, for example. So a lot of interesting things you can do with no ops. These are your arithmetic instructions, all pretty straightforward. Add, subtract, multiply, divide, negate. The main thing here is these instructions, of course, are going to affect the E flags register, and so what's good to familiarize yourself with is, okay, which flags do these instructions affect? And that's typically going to then come into play with if there's some operations and then some conditional execution statements. You need to be familiar with what flags may be set. So add, for example, the overflow flag could definitely be set as an example. These are your common binary logic instructions. Also, probably doesn't need much explanation. One thing I do want to point out is that you'll see this trick quite a bit in compiled code, this XOR EAX, EAX. This is just a really efficient way of assigning EAX the value 0, because anything XORed with itself, of course, is going to be 0. But this is both space and performance efficient, because it's essentially a 1-byte instruction that is doing a simple bitwise operation. You have your shift, logical, and arithmetic shift operands. Your load instructions. So here you're just loading relative or absolute addresses with LEA. Yeah, same with here if you're wanting to load a pointer from using the DS segment selector or the ES segment selector. These are the instructions you'd use for that. Compare instructions, these come up very often. The main difference is how the comparison is done. So the CMP is actually performed using a subtraction, and these are the flags that it sets, whereas the test is doing a logical compare. And so the most common thing that test is used for is actually if you're testing to see if a value equals 0, because it's if you're ANDing the two values and the result is 0, then it sets the 0 flag, and so it's kind of a quick and easy way of doing that check. And compare, of course, if you're testing to see whether a number is greater than or less than or equal to, then that one's a good instruction to use for that. Jump, this is just the unconditional jump. So if this instruction is encountered, then no matter what, it's going to take execution to whatever is its operand. So jump, you might see an address, you could see a register. In the case of a register, that makes life more difficult for the reverse engineer, especially if it's not obvious what value is going to be in that register. Other cases, it's a little bit more straightforward. If you're reverse engineering C++ code and you're dealing with vtables, it's more common that you'll find jump to some indirect register, because it may have the pointer to the vtable plus some offset that refers to a function that's to be called. These are all the conditional jumps. You'll notice there's quite a few here, so I'm not going to go through all of them. But again, if you check the reference manual, see what specific flags each of these jump instructions are checking on whether or not to take the branch. So quite a few. All right, the stack in x86, it grows downwards. So when you push value on the stack, you're actually subtracting 4 in this case. When you go to make a call, you're going to have the parameters pass the procedure, the return instruction pointer, and you'll see that initially the base pointer's pointed at that. Now typically what's done at the beginning of a call is you'll see push EBP, move ESP into EBP. And that's basically saving the previous base pointer and updating it so that you're creating a new stack frame for the current function. So this kind of illustrates what I just said about pushing and popping values. Pop is going to be incrementing it, the stack pointer, whereas push is going to be decrementing it. Other stack instructions to be familiar with: push A and pop A. This is essentially, push A is going to affect all of the general purpose registers. They'll all be pushed onto the stack. Pop A, they're all going to be popped off back into the registers. Enter and leave are basically creating a stack frame using the standard prologue and epilogue. If you look at these two sets of instructions, they're essentially inverse. So if you are pushing the base pointer and then assigning ESP to EBP, the exact inverse is then restoring the stack pointer with EBP and then popping the original base pointer back. So this is sort of, it's up to the compiler really whether it's using enter or leave statements. A lot of code may just, you'll see this routine, these first two instructions at the beginning of every call. Others you might see the enter instruction used, but they're essentially equivalent. As far as calls, like the majority of calls and returns are going to be, that you'll be dealing with, are near calls, but there are far calls. Typically those are calling into like operating system calls. And so the main difference between a near and a far call is what happens to the stack. In a far call, you're also going to have the current code segment register pushed onto the stack, and likewise it would be popped off the stack with the return, far return. And that's basic what I just said there. One other thing to note is that there is a ret_n instruction, which if you provided this optional n argument, then it's going to increment the stack pointer by n. So which is essentially a quick way of just clearing out parameters that may have been passed to a function. All right, so your far call and far return, as I mentioned, basically the same as the near call, except this is going to be pushing the current code segment and then loads the new one for the call procedure. And your far return is going to be doing the opposite. And then here's a diagram just to illustrate, in case that wasn't clear to you before. Here you see the stack in the near case has the parameters and calling EIP, and then the far call you the parameters, then the code segment and calling EIP. So, and then you also see down here what the stack looks like for the near and far return. And then here's another example. This is Ollie debug. And so you have some source code that was compiled. Basic program, just simply printing out some numbers. So here we see the call. It's pushing our arguments 1, 2, 3 onto the stack. And then we see here in the bottom corner, you see the return pointer to where once we hit red, it's going to go. And then also you'll notice the kind of the standard prologue that I mentioned, the push EBP, move ESP to EBP. The subtract ESP40, what that's doing is it's making room for local variables. It's essentially allocating space on the stack is what that's doing. And there's the string operations. These are a little bit more complicated just because they are using, to use these instructions, you're having to use multiple registers like ESI and EDI and EAX. The load instruction is going to be loading from ESI in the data segment to EAX, and the store instructions are going to be storing in EDI, the strings in EDI with the contents of EAX. So again, if I would refer you to the Intel manuals if you are going to be using these just to see the exact specifics of how they operate, but that's the general. Then we also have the compare and sort of scan string instructions if you're comparing strings in memory. These are quick ways of doing that. This is another instruction you'll see quite a bit, the repeat string operation. So this uses the ECX register it uses it as a counter, and it's going to essentially repeat whatever the string operation is ECX time. So if there's 5 in ECX, it's going to do whatever XX is. It's going to do that operation 5 times before it goes on. So again, this is a really fast way of doing string manipulations. The suffix on here, so rep NZ, that's repeat, well, not 0, repeat 0. Interrupt instructions, these are a special type instruction. Int3 is in particular important for reverse engineering. Int3 is the debugger breakpoint. So this is a CC hex byte. That's the opcode. And when you have a debugger attached to the program and you say, I want to break here, what the debugger is actually doing is it's overriding that byte with the value, the hex value CC. When execution encounters that CC, it triggers an interrupt, which your debugger handles, and that's how you get the program to stop. When you continue, you step forward, the debugger restores that original instruction, executes it. So each single step is essentially overriding the, it's handling each one of those exceptions. When you tell it to step over a function, it's going to overwrite the first byte of the return address with the CC. So basically, it will stop debugging, it'll run, and then it returns from that. As soon as it returns from that call, it hits that CC, and then you've got control again in your debugger. And 80 is another common one. This is for Unix system calls. If you want to understand what all these different interrupts do, then I'd refer you to either the manuals or operating system documentation to get a better understanding of what each of these interrupts are and what they mean. The ret I is the return from interrupt instruction. Again, it behaves just like the normal return instruction. And that concludes the overview. If you have any questions, feel free to shoot me an email, and we'll try to get back to you as soon as possible. If you have any, if you're wanting to explore it, I'd highly encourage you to check out the Intel manual, download it, flip through it. You'll get a better understanding of some of the more detailed nuances of the architecture, and it'll be a great reference once you start working on your first assignment as well. So Thanks a lot.